Hello, and welcome to Technically Speaking, where scientists and engineers come together to chat about a common interest, share knowledge, and satisfy some curiosity. I'm Laura, and I'm joined by Emma, Antonia, and Rwayda to talk about the crossover between physics and engineering. So, Emma, you're a physicist, so what drew you to that subject?
So I actually always really enjoyed physics at school, but what I actually enjoyed was the classes. I didn't actually associate that with me enjoying the subject. So when I carried on through my A-levels, I essentially just picked the topics that I really enjoyed the classes for. And so those were biology, physics, maths, and further maths. And then it came to university and I had to kind of make a decision. I really liked biology, but I knew that I wanted to carry on with maths, and I really liked physics as well. So then I just thought, if I do a physics degree, I'll have the option to do some biophysics there at some point, and I can still further my maths knowledge. So I just decided to do physics. No kind of rhyme or reason other than the fact that I just really enjoyed it, and I thought that it was challenging and that it doesn't close me off. I can still do stuff afterwards. So yeah, I'm very happy that I did that. It led me to do my PhD now, which has kind of gone away from physics a little bit, and it's a bit more in the biophysics, and I'm working on trying to find new anti-cancer drugs, and so I work a lot with DNA in the lab and also doing simulations as well.
You know, if someone had told me when I was deciding what to do at university that doing a physics degree could lead to me doing research that was looking at DNA and cancer treatments, I don't think I'd have quite believed. You'd have to explain what that is. I think we should do a follow-up episode on this, Emma.
Yeah, and how I got from A to B. Yeah.
And Antonia, you studied chemical engineering at university before you became an energy manager or energy analyst. So why did you choose chemical engineering?
I did a similar thing to Emma. I sort of went through school picking the subjects that I enjoyed and was good at. When I came to choosing a degree, I actually didn't want to do physics on its own or maths on its own or chemistry on its own. I thought, what would combine them all? And what would be interesting for me to learn? Because sometimes I'd struggle with studying. I think I was choosing between nanotechnology and nanoparticles, which I thought might be too specific. And then I came across chemical engineering when I heard that chemical engineers make things more efficient. I thought, okay. I think I started learning about climate change, and when we were in school, the amount of renewable energy there was in the UK was very, very, very little. So I thought if we could reduce the amount of resources we use, we could hopefully avoid climate change. And I'm still fighting that battle today.
I think what interests me there is you chose a degree that was very practical with an aim in mind to help society, which isn't something I considered when I was, again, choosing I basically sat there going, I'm quite good at textbook stuff. I have no clue what I'd want to do at university and just pick some random subjects. And you guys both sound like you were more strategic. Although Antonia thinks maybe not.
Well, there was another aspect which I didn't mention because it all sounds rather altruistic, was they also said if you graduate with a chemical engineering degree, the average salary is one of the highest you get as a graduate. And I didn't want to do finance.
Fair point.
So, was it all about climate change?
Fair enough. I guess we might get into that a little bit more because I also have thoughts on salary points for different degree types, and I don't think it is quite as clear cut as people say.
Yeah.
But Rwayda, you're a lecturer in civil engineering, so do you want to tell us a little bit about that?
Yeah, so growing up, I really wanted to do buildings, and for a very long time, I thought architect do the design. Little I know, they only do the drawing. But then later on, I realized it's actually civil engineers who deals with the design and the physics and the building and how the building behave and how the soil behave and how everything just combined together. So I decided to go with civil engineering, and it's also I did my degree in a different country, so my score dominated also some of my choices. I went with civil engineering, done that, enjoyed it very much, and I think that's why I stayed in academia, trying to get the next generation educated and get more engineers on the run.
Nice. Again, very noble aim.
Yeah, I just enjoyed building.
True, but from getting from that to teaching people as well as doing stuff with what you enjoy? I guess you enjoy teaching as much as you do the civil engineering aspect of it.
I think I do equally enjoy research and building, which is like I do some consultancy stuff and teaching, because I think I do enjoy people growing, because you could see how the student grow from their first year to their graduation. And I think this is just a pleasure to see usually.
Nice. I like the diversity that academia offers as well. When Antonia was saying engineers earn more, I think the route you're describing that you're currently on, Rwayda, is what scientists do in academia as well. You can consult, you can travel doing lots of research with different people, you can meet a lot of people, and you get that enjoyment of helping others develop as well.
Yes, the satisfaction of that actually. I don't know, it's a big part of why I stay in academia, because I kind of thought about transitioning to industry a few times now because everything comes with challenges. But I think I would miss on seeing that.
Nice. And I mean, I was an academic briefly. I didn't want to teach because I didn't feel like I had a thorough enough background in any one subject to be able to teach it well enough without first reading an entire textbook or 3. So I very much stuck to the research. But again, if you'd have told me when I was choosing my A-levels that I'd end up with the career path that I did, I also don't think I'd have believed that it would be this varied and this interesting.
But what's interesting there was just learning loads of different things is also a skill that I wish lecturers could also explain, because sometimes they understand a subject so well and trying to pick that up as a student is sometimes a challenge.
I mean, we're sort of talking about the crossover between physics and engineering, and we both picked very different career paths. And I suppose I probably cross over the most because I'm a scientist that works with engineers. And I couldn't really explain how I got into this. I just kind of ended up here. I think being in the nuclear industry really helped because I was a scientist working on this big chemical processing rig with lots of engineers and other people with different backgrounds. But I was very much into the hardcore science at school. I was like, physics is the hardest thing you can do, so I'll concentrate on that. I think that was quite a naive thought in hindsight.
Some people choose the easiest path, and some people choose to challenge themselves, and Laura chooses the absolute challenge.
Well, yeah, I started off doing it and then realised it's not quite the same as when you're doing it as at A level. As you pointed out, it's like trying to figure out the right thing for the right situation. And A level seemed like very well contained and niche, and I could understand how you'd get from there's a problem to there's a solution. But at university, I just sat there thinking, I don't understand why this is really relevant. You've got a particle in a well and you're trying to figure out where it is, and there's an equation to work it out, but I don't really see how the equation relates to the situation.
Yeah, well, this is exactly how I feel about engineering, is that it's great because you learn a theory and you know exactly why someone wanted to answer that question. You know, I want to find out how much energy this takes. And so they did all the maths to get there, and they had to do learning along the way. Whereas if I just had to learn from first principles, I think that I might not have actually ever got to the answer. Is that how you feel, Emma, that you feel driven to find out almost the absolute truth?
I think there was definitely a time in my life where I did think that when I started my degree. So a lot of it was very theoretical and learning, like you said, the concepts from first principles. But I think I really enjoyed that process because it really helped me to understand further down the line. Now I can move on to different things knowing I have this really nice background. And so I really liked the theoretical aspect of it. But then when I started to get to the end of my degree was when I was like looking more application and focusing a bit less on very like intense theory, because my route is very like applicable and practical. It's experiments and then real systems that you can see and have answers to, rather than very abstract particles or space that you don't really know what's happening. So I liked the initial theory aspects, but then now I'm like glad I'm rooted in some kind of quote unquote real things.
Generally, what I noticed from the student, they always don't see why we teach a certain thing. And they often miss with trying to teach them to problem solve more than anything else as an engineer, because yes, you might not get the same math when you go to industry or a company or something, but you will need the skill of, I have this problem and this is the route I will use to solve it.
Yeah, I come across that where in your sort of exam papers, they'll give you all the information or sometimes too much information to solve it. In industry, I found you have a lack of information. So you have to pick and choose what information will be easy to gather to roughly guess what you wanted the answer to. what you roughly wanted to answer in your question, because you don't get the perfect set of data, or it takes too long to get the data that you wanted.
Which is what scientists would like.
The thing that students mostly struggle with when I give them a coursework, not an exam, and I say use your engineering judgment to assume certain things, they hate that. But I think it's important to do it because that's exactly what you said in industry, and that's why we do it. You need to use your common sense, what we would call also engineering judgment, to find certain things and assume them so you can progress with that. So I'm glad you said that because it's a big thing that I notice usually students hate.
I can imagine if you're a first year engineering student, you've got very little experience in it. You wouldn't have a lot of engineering judgment. So I guess that's one of the things you say you can see improving as they go throughout the course.
Exactly.
How do you build engineering judgment? You know, it starts with understanding the principles first, or at least some of the theory behind it, right?
Yes, so you start with the theory, then when you throw them in the deep end and give them an open-ended coursework, they'll come and ask you questions, and that's what you encourage. Is like, these questions are important because what you would do usually, you respond to the question with another question. That other question is basically a hint to put them on the right way to think. Because you know the answer, you just don't want to feed them the answer.
Because you're not going to just get given the answer. You kind of have to figure that out, right?
Yeah, same in physics as well, I guess, once you get outside the textbook stuff when you're doing research. Rwayda, you said you wanted to be an architect and then you kind of realised that wasn't quite for you. So did you imagine that all this kind of using engineering judgment and having confidence in what you're saying would be part of being an engineer?
Yeah, because what I realized, like, architects are more on the art side and drawing and innovation in that way. And that's what not actually I enjoy. I do enjoy physics, and I enjoy using physics to solve things. So it just depended on my need of using maths and physics in a context of design and building rather than drawing that design.
I think it's interesting what you're saying about being interested in physics and using physics, because that kind of matches what Antonia was saying about physics involving a lot of theory and a lot of like fundamental principles. And I tend to think of physics as being, here's some principles or some maths essentially, or a way of understanding the world that we can apply in different ways to a particular situation. The simple example that I go back to, because I wasn't really good at physics at university, is A-level maths, when you do classical mechanics and you're resolving forces. So say you've got like an object on a plane and there's friction involved, and you can figure out how far you can tilt that plane before the object will start sliding or rolling or whatever it's going to do. So that's part of what you do, isn't it, Rwayda?
Yes, the very first thing we teach the student is the same concept, but we look at what we would call a beam and a support. So you look at, let's say, a bookshelf sitting on two ends on the wall. The load is your book, and then the piece of wood that holds it, or metal or whatever, is the beam. And that would deflect due to the load of the book. So you need to know how much you load it, how to stop underloading, like overloading it. And that all depends on the force dissolvance, because you change the books to a load, and that load will generate a reaction at what we would call a support, which is where the book will hold the ends. So it goes back to dissolving forces and action reactions, similarly to your talking about the plane and the friction. It's the exact same thing, it's just in a different context.
Yeah, and that's my understanding of a lot of the engineering that I've seen. But there's a lot more to it than just what I just said is A-level maths. There's way more to it than that.
You start building up, because that's like the stage one. Then you start getting the material itself involved. And then you start getting how that certain material react to that certain load. And until you graduate, you would have built a library of tools to use.
Can I also add that you guys are talking a lot about how you can use physics to do these things? And as a person with a physics degree, I feel like if I came across this problem, I would be a little bit like, I don't even know where to start. Because I feel like we learn a lot about the actual, like, we do apply it to new systems, but it's not so much of real applications. A lot of the physics problems are kind of like made up and fake to be easier or harder in a certain way, with not like a real exact application. So it's interesting to hear, because I feel like I actually wouldn't know where to start.
Maybe you could go to Rwayda and ask her questions, and she will ask you a question.
Put you in the right direction.
And you'll get there.
Yeah, that's true.
Yeah, we do a lot of physics, and it's not only to do with structures. We do a lot of other types of physics, like heat transfer. One of the things I done is looking at insulation materials and how that the material will react to a fire condition. So what happens to the roof if I have fire starting? How much the timber would char because of that fire? Then that would take us to needing to understand heat transfer concept. And how the heat moves through the building. I guess that's similar in other fields.
Well, there's some crossover there, but I'm less dealing with fire. When you said insulation, for me that's important in my job, seeing how much energy loss there would be if there wasn't insulation. But another part of the engineering is how much insulation do you need before you get diminishing returns, because there's no point installing like a foot of insulation when it could have achieved the same thing like 10 centimeters. So yeah, and that came from thermodynamics and fluid dynamics, which combined you kind of get the heat transfer. I remember a lot of maths actually, so there's definitely some links there for us, but a lot of symbols, less numbers. Mostly letters.
Yep, that's my memory of doing maths pretty much for the last 20 odd years. No one uses no one uses numbers. You do your equation and then just plug some numbers in using some software.
But that was something my lecturers would get really annoyed about. They would say, no, it wasn't the software that did it. You told the software how to do it because you know what numbers you're putting into the software.
Yes. Garbage in, garbage out, as they say. You have to understand what you're doing. You can't just shove some numbers into an equation and expect it to work.
Mm-hmm.
I mean, you can keep trying, but you might not know why it didn't go right.
Yeah, I mean, thermodynamics that you mentioned, so the study of essentially transfer of heat energy, that came up in my PhD. I said it was computational chemistry, but that was essentially solving equations for the forces between the particles. So equations of motion from physics, and then looking at how heat energy was moved around, because heat is essentially just particles vibrating, right? So a lot of my PhD, although I didn't realise it at the time when I first got into it, was about thermodynamics, but from a very different point of view. Rather than these big engineering structures, it was about individual atoms.
I suppose, yeah, there's the tiny scale and the big scale, and if we're looking at like the kinetic energy of particles, it becomes heat on a large scale, doesn't it?
Yeah, and similar thing, fluid dynamics was a bit of looking at shear forces in those simulations as well. Again, on a really tiny scale. I'm talking like less than the size of something you could see with a microscope. My simulations were that small.
It's funny you said like shear forces, because in my PhD I looked at shear forces, but when a column penetrated through a slab, so we dealt with the same kind of forces, but it just on a different scale.
Yeah, so I'd be looking at how my molecules would move around. So you'd apply a force motion essentially. So thinking of a liquid in a tank and you've got something stirring it, that would create shear.
I know a lot of people doing similar things actually in other physics PhDs, but more just generally I think in A-level and even high school physics, I think sometimes you talk about the Young's modulus of a material. So if you apply a force to it, how much does it stretch, and does that mean the material is elastic? So with an elastic band, you can obviously stretch it a lot and it will get a lot bigger, but some materials you can try and force them apart, but they actually won't move at all. And so I don't know if that comes a lot into engineering as well, because I can draw the plot and tell you where each different point is and what material properties it has, and maybe what that might be good for, but I don't focus too much on actually using those aspects of the materials.
Yeah, it does actually come, because it's one of the things we teach in the first year is stresses and stress strain, and for us it's actually important when they fail, or we say they fail, because when they change between elastic, you change the behavior and it goes back to its original state. Like if you think of a ruler and kept on kind of bending your roller until it gets to that point that this kind of white lines start to form. That means you kind of over deformed it until you got to the plastic region and started to fail. So lots of our design, we look at these concepts because we will put the steel and the concrete, but we don't want the building to collapse. We need to understand these properties in terms of how can I use them.
See, if someone asked me to just calculate the strain of something, but I didn't know it was in the context of maybe, preventing a building from being too elastic and stretching out, then I might not have tried too hard. But if this was my house and I had to calculate it, I probably would think very hard about how to do that well.
I guess a lot of the crossover here is really about maths. That's what we were talking about when you mentioned equations, Antonia. These are all just different formulae applied to different scenarios. In my undergrad, I said I was doing physics as part of it anyway. You had to do some maths alongside that in your first year, and you could either do the two pure maths components, two different modules, or you could just do a single module of maths for engineers, which is the minimum requirement for studying physics. So I chose to do that instead of the hardcore maths. I actually really enjoyed it.
Was it because it was more simple?
I honestly can't remember. It was that long ago. I remember I was really good at it. I think it might have been something about the way that it was taught that just made it really easy to apply it and easy to understand why the equation was the way it was. I genuinely wish I could remember more about it. It was Engineering Mathematics, I think, by Stroud was the textbook. Stuck in my head. It was that good.
Yeah. Oh, K.A. Stroud. Oh, he's like the engineering mathematics textbook that doesn't matter which discipline of engineering you did, you'd probably come across that textbook.
Sounds like a bit of a weird crossover for a physicist. There you go.
Yeah, I think I opted for the heavy duty maths in mine. But I really enjoyed that. Whenever I struggled to understand the theory, actually the maths really helped me understand what was going on. That's what I found saved me in a lot of exams.
That's good, because sort of my experience was like maths at school was quite A to B, and then we started doing more complicated integration, derivations, complicated maths techniques. And then Fourier transforms became part of it, and it was when I started to really get confused. It was like integration, but on another level. But I think it was useful for controls. So, in engineering, you have to precisely choose, are you going to add this much material? Are you going to move this much material? But then how do you tell a computer or some sort of automation to do that? You have to have some sort of control logic. And yeah, control logic, another field of maths, which can be quite complicated, but I imagine also quite rewarding, that you've basically automated a way to do exactly what you were expecting it to do.
Hopefully I can come in on the Fourier transforms as a person who's survived many years of doing Fourier transforms. I learnt it it's these series of equations. And so whenever we'd get asked it would be, I'm just going to apply these equations. But since then, doing my PhD, some of the data analysis stuff I use to analyze my lab work, which is images of DNA, has loads of Fourier transforms inside. And when it comes to the application, I have no idea what it's doing. It's a very complicated maths thing that I know exactly what it does, but learning the applications is almost like a whole other field of science to me, and something I really need to sit down and actually understand. I know it's used a lot in astro, because essentially what a Fourier transform does is it could take a signal which is very high frequency and convert it into a more readable signal. So if you have loads of background noise, it can separate out your true signal from the background noise really well, which is really great for communication and different aspects. So I see that application, but in terms of images to DNA, I'm I don't know what's happening there, but something is fixing my data and making it really nice. So I need to look into that though.
I think so. If you want to talk about it in your thesis, to say you applied it in this way, just if your examiner asks, did you really understand how you were doing this?
I know, and I think it's we're trying to get some work to go for a paper, and the theory section's going to be a struggle one to write, so I need to commit some time to learning it. But I know the basics. It's just the application I need to learn.
Fair enough. I mean, using it to look at DNA sounds kind of odd to me. So I've used it to characterize materials. It's used in spectroscopy. So basically, you shine a laser at your sample. You get a spectrum of light, so slightly different wavelengths from this one wavelength laser are reflected back to you. And the computer reads the signal, converts it into a useful graph using Fourier transform. So instead of all the noisy stuff that Emma mentioned, you end up with some, hopefully, really clear spikes on your graph. I honestly haven't had to look into how it does that in too much detail, because it's a standard set of algorithms, and I was using more the outcome of that rather than needing to understand in detail how it worked.
Like, I know Fourier transforms are in a lot of things, but because you've learned about them as well, it just made me think that there's a lot of maths that is coming up in different aspects of engineering. And that does make me want to ask a question that I really do not know the answer to. And that is, what is an engineer? I know it's a very broad question, but I feel like I don't really know what happens and what goes on.
I guess, given my weird career path that kind of spans engineering whilst being a scientist, I would say they do many, many different things. So when I was a researcher at university working on nuclear science, I was actually in an engineering department, and there was a component of project management in the civil engineering stuff that we were doing. So I was supervising some management of projects students in civil engineering, and you had to learn things like how to control the budget and the scope of a project and risk management and all these other things. So there's quite a lot to it, as well as the physics that Rwayda's mentioned.
Engineering is very, very diverse. And I would say, like, even civil engineering, which is a part, it has so many components. You could look at construction management, and that's when you manage the site and need to know when the material comes, how much that would cost, manage the budget, pay people. You're an engineer, but you're doing all of that because you're kind of like a project manager in a construction site. But also there is multiple other things you can think about, like drainage, transport, active travel routes. Everything is kind of designed by an engineer of a sort, most likely civil in these cases, but it's such a diverse world. And I think, because Emma asked, like, what would you classify an engineer? I think an engineer is someone take their knowledge and solve a problem in a simple definition.
Yeah, I guess I'd say there's lots of different components of knowledge that they draw on. Rather than a physicist saying, I'm a physicist and I do this, and engineers, I have all these different concepts in my head from engineering and project management and how people interact with something. So it kind of spans multiple different sciences, I guess. And you kind of draw a lot of that together to use scientific principles in a more cohesive way, I suppose.
Yeah, I definitely agree with Laura and Rwayda that engineering is quite diverse, and so the roles that people take can be quite broad. And yeah, science is part of your sort of the background, but then I don't know, it's like engineers sort of almost like are put on to what they are trying to solve. Like civil engineers are trying to solve how society functions, how they have buildings, how they move around places.
How to make chemicals.
And what are the chemicals for? Are they for making the buildings, for washing, for energy?
Making food.
Making food, yeah, that's a good point. Like, one of the big research areas at my university was food and cereal, which I wouldn't have initially thought was about chemical engineering, but it was, you had to manage like powder, how that can cause fire, and how do you bake food on a industrial scale and things like that. I think that's what I found interesting about chemical engineering is, again, because it's so diverse, you could end up being more like a material scientist, researcher, or in my case, sustainability, and trying to figure out the problem of everyone needs energy, but we need to do it in a way that is sustainable.
I'm guessing you probably didn't study as much project management in the same way that Rwayda did, and that I'm aware of from being in a civil engineering department, because you're a chemical engineer. But I guess it probably still comes up in the work that you do, because you work with clients and energy intensities and things like that, and figuring out whether they should make a change to their process or not.
So when we're first designing like a chemical plant, you kind of figure out the basic route of, like, say, synthesis, because there's different routes. You might use one raw material versus another. That usually comes from some research a chemist did, figuring out whether you could actually scale it up. That was like a core part of what we call design. Now, I do a bit of project management in the sense that before they do the project, I'd figure out what they need to know to make a project happen. So that might be the practical aspects of how long will the project take? How soon could it happen? What disruption might it cause on their site? Because a lot of my customers are manufacturing, and every day you're not using your machines to manufacture stuff is expensive. So you want to sort of minimize downtime, but you also need to maintain equipment, things like that. So a lot of other aspects of practical things that you might not think about, like physically, where does all the pipe work go? Where does the equipment go? And so sometimes there's a bit of like rearranging stuff on site. At the core of my role would be gathering how much energy does this thing use in the first place? So how much opportunity is there to save? And does that kind of balance out with the cost of implementing this solution? Because if it costs way too much and it's not even going to pay back in anyone's lifetime, it's quite hard for a company to decide we're going to put that much money in.
There's a bit of parallel there between if you're gathering underpinning data to decide if a project is feasible. It's a little bit like using fundamental theory or the principles from physics to do something more, do something extra, come up with a new theory, do some new research, something like that, if you're a scientist.
Yeah, definitely. A lot of the stuff I did at uni was quite theory based, and you'd get a lot of like equations to understand it. But then I go onto site and engineers are much more practical. They have trousers with lots of pockets to hold lots of different tools. And they do maintenance, the welding, wiring, plumbing, basically the skilled tradespeople.
I mean, I like doing DIY stuff at home. I'm definitely a big fan of maintaining my own road bike. So in that respect, I'm kind of like you're the typical tradesperson you just described. But I still say the theory is pretty useful. Putting my scientist hat back on. So a lot of civil engineers that I worked with in the nuclear industry had desk jobs doing things like designing parts of nuclear reactors. And you get physicists in the nuclear industry too doing things like working out geometries of reactor cores. So the theory is actually really, really useful.
Exactly. I was just going to add when you mentioned that you're fixing everything up. I feel like, Laura, I'm just never surprised by the new things that you do. You just seem to cover absolutely everything. It's crazily impressive. But I was wondering if you guys had anything to contribute to the debate of physicists versus engineers, because I feel like I grew up watching a little bit of the Big Bang Theory, which is kind of a miracle. I ended up doing physics after watching that. But that was like a huge debate in the show, and I don't know if I carried that forward a little bit throughout my degree, and I heard a few like comments where people be like, oh, engineers like to say that pi is 3 and g is 10, and very like rounding and non-specific, whereas we're like it's 9.81 something something. But yeah, I just was wondering if there's anything to add to that debate.
It's not a result unless you've got error bars. That's what I was taught as a physicist.
Yep, exactly.
Yeah, engineers have tolerances, which is effectively the same thing. Like, we know this beam will fit this gap with this much difference in the gap.
We also use sensitivity analysis. I mean, people also use it in sort of financial terms of like, if this changed by 10%, how much impact does it have on the final result? If that difference between 9.81 and 10 does not influence the final result, we can drop the decimal places, surely.
Counter that point, Emma, physicists make approximations too, don't they? You assume everything's a sphere and it's in a vacuum, and air resistance just means nothing to you.
And travelling at the speed of light.
Yeah.
Yeah. I mean, we do have an approximation. When I got to my third year of uni, everyone's like, G is not 10, it's 9.81, but then we get to uni and you set the speed of light equal to 1. Because it's just like out of the equation, but apparently physicists are fine with that, so I think they're picking and choosing their battles with the approximations.
I will say, I don't come across that many physicists in my job anymore, so people aren't coming at me saying, we approximate too many things. If anything, I get people who are not scientific or engineering background at all and saying you're going into too much detail. I just want to know a yes or no answer.
Similar-ish in science communication. I've either not got enough detail to satisfy the scientists, especially the physicists, or I've got too much detail and I've lost my audience because they don't care about the detail. I think what we're saying, though, is labels don't necessarily matter. We're all working towards effectively the same thing because we all have shared interests, which is why we're talking to each other. So we all seem to care about climate change and educating people and helping each other out. So we're all effectively doing the same thing, just with a different approach.
Yeah, and the diversity of our backgrounds and expertise all helps.
Exactly, yeah. Seeing a different problem from different angles helps lead to better solutions. I think I've just found an excellent line to end the podcast episode on. So as you say, we've all got different career paths, different reasons for choosing them, and there might be some rivalry, but ultimately we're all doing the best we can to contribute to the world. Thank you all for listening, and we will see you next time. The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.